some of the problems from the review packet, I think I just want to do the hardest ones and maybe do a sampling from each section. I don't think I want to do the entire thing. I kind of put some of the hardest problems first, and actually these first few problems are some of the trickiest ones that there are. So this one here, inverse sine of pi over 6. Whenever you have a composition of trig functions, I recommend that you pay close attention to what the inside expression is. That is a regular trig function, sine of pi over 6. We can actually evaluate that. Sine of pi over 6 is the y-coordinate associated with pi over 6. What is that? Well, let's see. Pi over 6 is like the small angle. It is more over than it is up, which means that the x-coordinate is larger than the y-coordinate, which means the x-coordinate is root 3 over 2, and the y-coordinate is 1/2. So the sine of pi over 6, the y-coordinate is 1/2. So this is inverse sine of 1/2. Okay, so I've just replaced sine of pi over 6 with 1/2. Now, okay, now what do I have to do? Now I have to evaluate inverse sine of 1/2. Well, what is this? This is an inverse trig function, and of course what an inverse trig function produces is an angle, right? This is an angle whose sine is 1/2, right? There are lots of such angles, and pi over 6 is certainly one of them, but it's not the only one, right? There's another angle over here which also has a y-coordinate of 1/2. I guess that would be 5 pi over 6. So which one is it? Is inverse sine pi over 6? Is it 5 pi over 6? Is it something else? Well, that's where you have to remember that the inverse sine function has a restricted range from negative pi over 2 to pi over 2, so we have to choose the angle that actually sits within that interval. 5 pi over 6 is too large. It's bigger than pi over 2, so forget about that one. This one, though, is good to go. That one's actually in the interval. So the answer is pi over 6. So this whole thing just winds up being pi over 6, which is perhaps not surprising because you're sort of composing a function with its inverse, not shocking that the sine functions cancel. Let's have a look at this one. Again, I recommend you start by evaluating the inside expression, sine of 7 pi over 6. What is that? Well, we just a moment ago recalled the coordinates of pi over 6, right? Pi over 6 had the coordinates root 3 over 2, comma 1/2, and we saw that the sine of pi over 6 is 1/2. Now 7 pi over 6 essentially has the same coordinates as this thing, except, of course, some of the coordinates could be negative. Where is 7 pi over 6? Well, 7 pi over 6 certainly is larger than pi. It's just a little bit larger than pi, which means it's just halfway past, it's just a little bit past this halfway mark, this pi mark here. So 7 pi over 6 is perhaps down here. The coordinates of this point will be the same as the coordinates of this one, but of course being in the third quadrant, both of the coordinates must be negative. So it's negative root 3 over 2, comma negative 1/2. So the y-coordinate of this point is negative 1/2. So this inside expression here is negative 1/2. So what we're really looking at here is inverse sine of negative 1/2, right? Okay, well, what's the inverse sine of negative 1/2? Well, that, of course, is an angle whose sine is negative 1/2, right? So what are some angles with a sine of negative 1/2? Well, obviously 7 pi over 6 is one such angle. But it's not the only angle. For example, if you look at the unit circle, 11 pi over 6 also has a y-coordinate of negative 1/2. Which of these, and how do you choose between the angles? Well, you have to remember the restriction on the inverse sine, which I have over here. We have to choose the angle which actually sits within that interval. Which of these sit within this interval? The answer is neither of them. They're both too big, right? They're both bigger than pi over 2. If you look at where these angles sit on the unit circle, 7 pi over 6, we just said, sits right here. 11 pi over 6 sits over here. This angle here, 11 pi over 6, is sort of in the right location on the unit circle, right? Like it's on the right side of the unit circle, but it's the wrong representation of this angle. So what is the correct representation of this angle that actually does sit within the restricted range for inverse sine? The answer is negative pi over 6, right? Negative pi over 6 sits here, same location as 11 pi over 6, but this representation of that angle actually sits inside that interval, inside the restricted range for inverse sine. So sine inverse of negative 1/2 is negative pi over 6, okay? Cool. 1C is a really tough problem conceptually, and just to make things extra stupid, there's a mistake in the solutions. The solutions say that the answer was 90 degrees. It's not. It's actually 80 degrees. So sorry about that. Let's see why it's 80 degrees. This is really tricky. I went over one like this in class. Basically, the idea is the following. Sine of 100 degrees, I don't know what that is. 100 degrees is not an angle on the unit circle. But thinking about it, 100 degrees is like a little bit past 90 degrees. And the sine of 100 degrees is just the y-coordinate of that point. I don't know what the y-coordinate of that point is, but, it's pretty close to 1 because that point's pretty high up. Let's say that it's, 0.9. It isn't really 0.9. I don't really know what it is, but it's something like that, okay? So let's pretend temporarily that sine of 100 is 0.9. So we're looking at the inverse sine of 0.9. So what is this? Well, of course, this is an angle whose sine is 0.9. Well, what angles have a sine of 0.9? Well, 100 degrees, the angle we started with obviously has a sine of 0.9. That's for sure. But 100 degrees will not be the answer because the inverse sine has a restriction, right? It only produces angles between, well, as measured in degrees, negative 90 degrees to 90 degrees. So the inverse sine of this thing cannot produce 100 degrees because that angle is just too big. So forget about it. We need a different angle whose sine is 0.9 but actually sits within the restricted range. If you think about it, that angle over here will have the same y-coordinate as this one, but will actually lie within the restricted range, and that's 80 degrees, right? 10 degrees less than 90, so the correct answer is 80 degrees. Okay, moving on, let's have a look at D. So here, if you look, the composition is a bit reversed. In the first three problems, the inverse function was on the outside, inverse function on the outside, inverse function on the outside, but here the inverse function is on the inside. As always, I recommend that you think about what's on the inside of the expression first. So inverse cosine of 0.735, well, what is that? Well, since this is an inverse trig function, that's an angle. This thing that I've underlined is an angle whose cosine is 0.735. I definitely don't know what that angle is. Okay, like I don't know any angles that have a cosine of 0.735. I certainly don't know. So, I don't know what that angle is, but what am I doing with this angle? I'm taking the cosine of it. Okay, so this is an angle whose cosine is 0.735, and I'm taking the cosine of that angle. By definition, I have to get 0.735, okay? So the trig functions sort of cancel in that circumstance. Okay, the first four problems on this worksheet, I would say, are probably some of the trickiest in the entire review. So I don't want you to be panicked. I kind of put those first so that you'd be working on them in class, not at home, and we'd be able to talk about them. Now we get into some slightly more conventional stuff. This is what I would call a more conventional composition problem, right? So here the trig functions are mixed. And I'd say when they're mixed, it's actually kind of easier to think about. So start by looking at the inside expression. What is that? Well, it's an angle, right? Inverse trig functions produce angles. So this thing is an angle whose cosine is 3/5, right? Okay, great. Do you know any angles whose cosine is 3/5? Yeah, I don't either. So I don't know what this angle is, so I'm just going to call it theta. Now, the basic idea is you draw a picture of theta and then use some right triangle stuff to find its sine. So we know that the cosine of this angle is 3/5. That's a positive number. Since the cosine of the angle is positive, that means that theta is either in this quadrant or this quadrant. Now, the other thing is the inverse cosine function has a restricted range. It's from 0 to pi. It can only produce angles between 0 and pi. That's this quadrant and this quadrant. So those two considerations, the fact that the cosine of the angle is positive and the fact that the inverse cosine function has a restricted range, means that this angle actually has to sit in the first quadrant. So that's where my angle theta actually is. Now, knowing that the cosine of this angle is 3/5, I remember that the cosine is defined as x over r. Apparently x is 3 and r is 5. So if I draw a circle of radius 5, then the x-coordinate of this intersection point will be 3. And I can, of course, so let's remember what I'm trying to do here. I'm trying to find the sine of this angle, the sine of theta. And the definition of sine is, of course, y over r. Well, I already know that r is 5, right? I've just found that from here. I just have to find y, which means the y-coordinate of this point right here, which you can find doing right triangle trigonometry. Drop a perpendicular line to the x-axis. What do we know? We know that this side is 3, this side here is y, that's our unknown, and this side here, that's a radius of the circle, which we just said was 5. So if you do the Pythagorean theorem, 3 squared plus y squared is equal to 5 squared, you should find that y squared is equal to, let's see, 25 minus 9, that's 16, so you get y is equal to, I guess, plus or minus root 16 or plus or minus 4, but in context it's clear that the y-coordinate of this point, since this angle is in the first quadrant, the y-coordinate should be positive, so we get positive 4. So finally, what is the sine of this angle? Well, it's y over r, which we just found that y is 4, so 4 over r, which is 5, so 4/5. And just a quick check, should it be 4/5? Are we really sure that it should be positive 4/5 and not say negative 4/5? Yeah, because this angle sits in the first quadrant and the sine function is positive there. So the sine of that angle should be a positive number, okay? F is very similar. G is very similar. Just use the hint. Rewrite negative 0.5 as negative 1/2, and then, it pretty much comes out the same. What else do we have here? Okay, now we come to a lot of inverse trig function evaluation problems. I just want to remind you how you do this. Inverse sine of 1/2, that means you're looking for an angle whose sine is 1/2. Well, there are many such angles. In fact, there are 2 of them on the unit circle alone. One of them is pi over 6, that has a sine of 1/2, and the other one is 5 pi over 6, which sits over here. They both have a y-coordinate of 1/2. Which of them is the correct answer? Well, it's whichever one sits within the restricted range for inverse sine, which is negative pi over 2 to pi over 2. And pi over 6 is the one that sits within here, so that's the answer. On the other hand, inverse sine of negative 1/2, we already did this one earlier, but I'm going to do it again because it's so important. You're looking for an angle whose sine is negative 1/2. So you're looking for an angle whose y-coordinate is negative 1/2. I can think of 2 angles on the unit circle which have that property. One of them is whatever the pi over 6 guy is here. I guess that'd be 7 pi over 6. And this angle over here, 11 pi over 6, those both have a y-coordinate of negative 1/2. Which one do you choose? Well, the one that sits within the restricted range for inverse sine. Which of these sit within that restricted range? The answer is neither of them. They're both too big, right? They're both bigger than 1/2 pi. However, if you remember negative pi over 2 to pi over 2, if you plot that, it is the right-hand side of the unit circle. So this angle here sits in the correct location. It's on the right-hand side of the unit circle, but it's the wrong representation of that angle. So it's not 11 pi over 6, but rather negative pi over 6. Negative pi over 6 sits in exactly the same location, but has the advantage of actually sitting literally within that interval. So the answer is negative pi over 6. Let's do one of the tangent ones, inverse tangent of 1. Hopefully, so what is this? This is an angle whose tangent is 1. Hopefully you recognize that that's some kind of a pi over 4 thing, right? It's at the pi over 4 angles that the tangent is 1 because the x and y coordinates are essentially the same. I can think of 2 angles on the unit circle which have a tangent of 1. One of them is pi over 4, and the other one is down here where both the coordinates are negative, both the x and y coordinates are negative, because then y over x, which is what tangent is, would still be positive 1. And that would be, 5 pi over 4, right? Now, which of these angles is it? Well, it's the one that sits within the restricted range for inverse tangent, which is the same as the restricted range for inverse sine. Pi over 4 sits within this interval, this one doesn't. Okay, so that's enough of the inverse trig functions. These guys here, converting between, radians and degrees. Hopefully you remember, to convert from degrees to radians, you just multiply by pi over 180 and simplify. To convert from radians to degrees, you just multiply by 180 over pi and simplify. Okay, moving on. These are just straightforward unit circle values. This is just checking, do you know your unit circle values? Moving on, let's see. Number 7, theta lies in quadrant 2, and sine of theta is 2/5. Find the cosine of theta. Well, you know, this is kind of an easier version of problems we've already done. Theta lies in quadrant 2, so it's over here, and the sine of theta is 2/5. Sine of theta, of course, is defined as y over r, so apparently y is 2 and r is 5. So if I draw a circle of radius 5, then the y-coordinate of this point is going to be 2. Now I'm trying to find, there go the lights. Now I'm trying to find the cosine of this angle, which of course is x over r. I already know the r value is 5, so I just need to know x, which is the x-coordinate of this point, which you can do by making, you know, a right triangle. Just, you know, bear in mind that your x value is going to be negative because this angle sits in the second quadrant. Okay, always remember that. Find an angle theta in the third quadrant such that cosine theta is equal to cosine 193. Where's 193? It's like down here, okay? Oh, this doesn't make any sense now that I'm looking at it. That should say something else. That should say second quadrant. Okay.